Welcome back. So far in this section we have discussed multiple design considerations for thin film solar cells. In this video we will discuss another important concept for thin film technologies, multi-junction devices. To create a good understanding of multi-junction devices, we will learn about the spectral utilization of a device with multiple junctions. We will discuss the output characteristics of such a device, and we will look at the interconnection of the multiple junctions and how that affects the Venn diagram of the device. We start with the spectral utilization. Shown in this figure is the AM1.5 spectral power density as observed on the surface of the Earth. As you may recall, any single junction solar cell can only utilize a fraction of the available energy. This fraction is indicated by the brown area for a certain bandgap energy. Depending on the bandgap energy of the absorber, a fraction of the energy will be lost either due to non-absorption of photons or due to thermalization. The spectral utilization of a single junction solar cell is described by this equation. In the denominator, the product of the photon energy and photon flux is integrated over all wavelengths, effectively representing all available energy. In the numerator, the photon flux is multiplied by the bandgap energy to consider that energy above the bandgap is lost due to thermalization. Moreover, the product of the photon flux and photon energy is only integrated up to the bandgap wavelength, taking into account that photons with an energy below the bandgap are not absorbed. The usable fraction is also known as the ultimate efficiency of a single junction solar cell, as it only considers the spectral mismatch of the cell. Another limit for solar cell performance is the Shockley-Queisser limit. The Shockley-Queisser limit will be discussed in more detail towards the end of this course. For now, it is enough to understand that the Shockley-Queisser limit also considers those recombination losses that are fundamentally required. For a single junction solar cell with an optimal bandgap energy of 1.12 electron volts, the ultimate efficiency is about 48%, and the Shockley-Queisser limit is roughly 33%. If we introduce a second junction, the thermalization losses in the visible part of the spectrum are strongly decreased. An optimal tandem configuration has a junction with a bandgap energy of 1.74 electron volt and one with 1.16 electron volt bandgap. The ultimate efficiency of such a tandem device is increased to over 65%, and the Shockley-Queisser limit is increased to almost 46%. If we introduce a third junction aimed at the infrared part of the spectrum, we can strongly decrease the losses due to non-absorption. An optimal triple junction device has an ultimate efficiency of 73.5% and a Shockley-Queisser limit of over 51%. The origin of the performance increase can be visualized by this Venn diagram of a semiconductor. We illuminate the semiconductor with a full spectrum of photons. All photons with energies above the bandgap are able to excite electrons from the valence band to the conduction band. The green and blue photons, however, are excited high into the conduction band, which means that they have a large amount of excess energy. This excess energy is lost due to thermal relaxation. Now, if we have the same incidence spectrum, but with 3 semiconductor junctions instead of 1, and with different bandgap energies, the amount of excess energy is strongly reduced. Consequently, the ultimate efficiency of the device is increased. But what does the actual performance of a multi-junction device look like? Let's look at the current voltage characteristics. This figure shows the JV curves of 3 single junction devices with different bandgap energies. If we integrate these 3 junctions into a single multi-junction device, the resulting JV curve depends on the device configuration and interconnection. The blue junction is the highest VOC and the lowest JSC, which means that this junction has the highest bandgap. In contrast, PN junction 3, indicated by the red curve, has a low VOC and high JSC. Consequently, this junction has the lowest bandgap. The spectral part with the most energetic photons, like blue light, has the smallest penetration depth in materials. The junction with the highest bandgap therefore always acts as the top cell. In this way, the most energetic photons are absorbed with minimal thermalization losses, and the top junction is effectively transparent to a large fraction of the spectrum with photon energies below its bandgap. Before we can draw the JV curve of the resulting triple junction cell, we must consider how the junctions are connected. We will look into how different junctions in a multi-junction are connected in the second part of this video.